Good morning, students, and welcome you all to this section. This is your instructor, Sir Isaac, Mathematics Department, Akuse Methodist Senior High Technical. In this video, we shall look at the section 2 of our mathematics learner materials, fractions and percentages, number for everyday life, proportional reasoning. So let's start with the introduction. In this section, we are going to explore the fascinating world of fractions. Fractions are a fundamental concept in mathematics that represents parts to whole relationship, a part to the whole relationship. Understanding fractions is crucial for problem solving in various aspects of life, from even your normal cooking and shopping to science and even engineering. The concepts and operations of fractions. In this lesson, we will delve into the concept of fractions, learning how to perform operations like addition, subtraction, multiplication, and division, and even apply these skills to real-world scenarios. You will discover how fractions connect to other mathematics topics such as decimals, percentages, and ratios. Now let's start with the concept of fractions. A fraction is a concept which represents a numerical value and defines parts of a whole or unit, a group, or a ratio. So an example is if you take the human body, when you take the human body with your eyes, your nose, and even your mouth, you realize that the whole is your body. But if you take, for example, your hand becomes just a part of the body. So we are saying that the hand here is called a part, and the whole body is the whole fraction, that is whole. So whenever we talk of fraction, we are looking at parts to whole. So what part? The hand to the whole body becomes a fraction. So hand over body becomes a fraction. So let us look at this very figure here. You are seeing this figure here. Let me even enlarge it for you to see it clearly. When you take this, you realize that it is a circle, and this circle has been divided into four parts or four quadrants. Now you can see one part, you can see another part, you can see another part, and you can see another part, making it four different parts. Good. Now, so they are all one, 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 one. Let me use one to indicate that they are all one out of the four parts. So for example, if I want to pick this very part, if I take this part becomes just one of the total 4 parts. So this is what we call the part 1, and that is the numerator. Then the entire figure becomes what we call the whole, and that is the 4. So it is just 1 out of the entire 4, and that becomes a fraction, 1 out of 4. That is the basis for fraction, or the concept of fractions. Now let's move on to the next part. Fractions include 2 parts. So whenever you have a fraction, it includes 2 parts, the numerator and the denominator. So what is the numerator? The numerator is the upper part of the fraction that represents the number of sections of the fraction. So for example, when I take back this to the next page, we can all see that, okay, so let's take this here. We are saying that the upper part, this is what we call the upper part of the fraction, and the technical name is the numerator. Then this value is the lower part, and the technical name for that is the denominator. So for example, when we pick this fraction 3 over 4, 3 over 7, we are seeing the upper part to be 3, and that is the numerator. Then we have the lower part of 8 being the denominator. All right, so let us move on to the next page. That is types of fractions. We have different types of fractions, and we shall look at all of them as we move on. The first type of fraction is a proper fraction. When do we say a fraction is proper? Proper fractions are those where the numerator is less than the denominator. The numerator is less than the denominator. In our previous section, we looked at the numerator and the denominator. So here we are saying that for a fraction to be proper fraction, the numerator must be less than the denominator. So an example is 3 over 7. This is the numerator n, and this is the denominator d. And we can see clearly that the numerator is less than the denominator. So if this condition is met, then the fraction becomes a proper fraction. So take your time and write 5 more fractions whereby the numerator is less than the denominator, and group those fractions as proper fractions. Another example is 2 over 5. We can see that the denominator, which is the numerator, which is 2, is less than the denominator, which is 5. Our next type of fraction is improper fractions. Improper fractions are fractions where the numerator is greater than the denominator. So in this case, the denominator, or the numerator rather, is greater than the denominator. So it is just the reciprocal of the first. So an example is going to be 7 over 3. Here we can see that the 7, which is the numerator, is greater than the 3, which is the denominator. And that makes it an improper fraction. The next type of fraction is the mixed fraction. When we say mixed, it means that we are trying to merge a whole fraction to another proper fraction. We are merging a whole number to a proper fraction. So we have mixed a whole number with fraction, and when that happens, the fraction is called mixed fraction. Mixed fractions are a combination of the integer parts, that is a whole number, and a proper fraction. These are also called mixed numbers or even mixed numerals. So an example is to pick a whole number 1 or an integer 1. Then I add to a fraction, a proper fraction, which is, let's say, 1 over 2. Then I'm going to have one whole number, 1 over 2. And such fraction is called a mixed fraction. This part is the integer part. The integer part, and this part is the proper fraction. And it is proper in the sense that the numerator is less than the denominator. So we have examples of mixed fractions. 5 whole number, 3 over 7. 5 whole number, 3 over 7. This is the integer part, and this is the proper fraction. We have 1 whole number, 2 over 3, 9 whole number, 2 over 3, 8 whole number, 11 over 12. These are all mixed fractions. Now let's move on to the next one, which is the like fractions. Like fractions. When do we say two fractions are alike? These are fractions that are alike or the same. For example, take 1 over 3 and 2 over 3. They are alike since they have the same denominator. So here we are saying that two fractions are alike. They are like fractions if they have the same denominator. So when I take 2 and I divide by 3, if I take 4 and I divide by 3, then for the fact that these two fractions have the same denominator, we can conclude that the two fractions are like fractions. I want us to take your time as students and write 5 different fractions, two pairs of fractions that are alike. That are alike. Let us write one more. So I can write 4, or let's take let's say -1/2. Then I have, let's say, 7/2. These two fractions are alike. They are alike because they all have the same denominator. Good. Now let's move on to the fifth type, which is unlike fractions. Unlike fractions. Unlike fractions are those that are dissimilar. They have different denominators. So it is just the reciprocal, or it is just the negative of the like fractions. Whenever you have a fraction with different denominators, then those fractions are unlike fractions. So when we take the unlike fractions, we can have an example to be 3/5. Then we can have, let's see, 4/9. These two fractions are unlike fractions because the denominators are not the same. You can even have unlike fractions with numerators being the same. For example, we can have 5/6. Then we can also have 5/7. Even though the numerators are the same, the denominators are still not the same. And for that matter, these two fractions are unlike fractions. Take your time and write two pairs of fractions that are unlike. The tip is that ensure that their denominators are not the same. Now let's move on to the sixth type, which is the equivalent fractions. Equivalent fractions are fractions that represent the same value or proportion even though they have different numerators, top numbers, and the denominators, bottom numbers. So in other words, two fractions are equivalent if, when simplified or converted, they equal the same fraction. So let's get this one very clear. When we say fractions are equal, their denominators and numerators may differ, but its value may be the same. Let's take an example to be 3/5. And let's also take another example to be, let's say, 6/10. Let's compare these two fractions. They all have different numerators and they also have different denominators. But the two fractions have the same value. Now, they have the same value because if you have 10 people, let us say we have 10. Let's group this 1. Okay, let me divide this into 10 and explain the concept here for clarity. Let's say we have 10 boxes. 1, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last one should be 10. So we have 10 boxes here, and all the 10 is making the whole rectangle. I can shade 3 of them. Let's say I shade this region, and even shade this region. Sorry. Or let me take the first three. Let me take the first three. When I take the first three, it means I have shaded 3 out of the entire 10. But note that this whole figure can be divided into 2. So if I divide this into 2, then it means that this 3 out of 5, we have the whole fraction, which is 6 out of 5. The whole fraction is 6 out of 5. So I can also shade another 3 here. Let's shade another 3 here. 1, 2, 3. So you realize that in the 10 boxes, we have shaded 6. So the part that we have shaded is 6. And that is the numerator. And the whole is the entire boxes. That is making the rectangle. And that is 10. So how many have we shaded? 6 out of how many? 10. That is correct. Now, if I should divide this whole rectangle into 2, if I divide it into 2 equal halves, then you realize that I am now going to get a whole of 5 for one part. And out of that whole, it is only 3 that has been shaded. Therefore, we can get 3 out of 5. Then the other part, we also have 3 out of 5. So it means that the value of this is the same as this. That is when you divide both the numerator, that is the part, and the whole by half, then you will get back this whole fraction. So half of the numerator, half of the denominator will give us 3 on 5. And that is equivalent fraction. So when you take the whole to be 10, its numerator has to be 6. But if I should reduce the whole by half, then it means that the part, which is 6, has to also be reduced by half for us to get 3 out of 5. So this value and this value are the same, even though their numerators and their denominators are different. And that makes it an equivalent fraction. So example is 1 on 4 and 2 on 4. When we pick 1 over 4, 1 over 4, sorry, it's 1 over 2. 1 over 2, and we also pick 2 over 4. You realize that this 1 over 2, when you multiply the numerator by 2, and you also multiply the denominator by 2, 1 times 2 gives you 2. And 2 times 2 gives you 4. So it is the same. The other concept is that imagine when you take 1 over 2, it is just like having 2 oranges. Having 2 oranges. And you want to share these 2 oranges. Sorry, you have 1 orange. Just 1 orange. Let me use a circle for clarity. So let's say you have a circle here, just 1 orange, and I want to share this orange for 2 people or 2 students. Then the best thing to do is to divide the orange into 2. If I divide the orange into 2, then it means that there are going to be 2 parts. 2 parts. So the one person will get just 1 out of the 2 parts, and the other person will also get 1 out of the 2 parts. And that is the basis for 1 over 2. It means that divide a whole, that is 1, by 2 and take one of it, take one part of it. Then this same fraction, if I should divide it into 4, rather, if I should divide this into 4, remember that the half, which is this part, is the same thing. This part, which was half of the 2, has now become 2 parts of the entire 4 divisions. So we are saying that this same region, which was once one part of the 2 divisions, has now become 2 parts of the 4 divisions. So we are saying that 1 over 2 has now become 2 parts of the 4 divisions. So 1 over 2 and 2 over 4 are basically the same fraction, and that is an equivalent fraction. So let's look at this. So that is for the equivalent fraction. Our next type is going to be a unit fraction. A unit fraction. When we say a fraction is unit, it means that the entire whole or the entire fraction is taken as one, and it has been divided into various parts. So the numerator should always be 1. For a fraction to be unit, the numerator has to be 1. So an example is 1 over 20, 1 over 7, 1 over 5. All these fractions are unit fractions because their numerators are 1. Think of more unit fractions and write them down. Now let's look at some application of the concept of fractions and examples. Now I will entreat you to go through this activity 2.1. We were supposed to carry out this in schools, but since you are in your various homes, I will entreat you to carry out this activity. So the first one is to model and represent fractions using a number line. A number line, paper strips, or even the Cuisinart rods. So you can use these to model fractions. So we are going to take you through this so that you can try more examples on your own. So the first part A, we are representing fractions on a number line. On a number line. So let's look at this number line. The number line has been divided into 1, 2, 3, 4, 5. So we have 5 divisions. We have 5 divisions. So we are starting from 0 and we are ending at 1. So let us divide. You realize that if you should move from 0 to this, you have moved one journey. Then your second distance is this, your third distance is this, then you make the last move to your destination. So from 0, so it means that the entire journey has been divided into 4 different parts. 4 different parts. So it means that moving from your initial point, that is your origin, to your destination, you have to first move 1 out of the entire journey. Then you move 2 of it, 3 of it, then you move 4 of it to your final destination. So starting from 0, if I move from here, so it means that in your initial stage, you have not moved. So you have just 0 over 4. And 0 over 4 is the same as 0. Then now you move 1 unit. When you move 1 unit, you have just moved one out of the entire 4 parts. So 1/4. Then when you move from here to here, it means that you have moved twice of the entire distance, which is 4. So 2/4. Then when you move again from this point to this point, then it means you have moved 3/4. And finally, if you move from here to here, then you have completed the journey by moving 4/4. And we know that 4/4 is 1. And that is the interpretation of this number line. Let us also look at this. Here, let's count the division of this journey. First, we have the first part of the journey here, second part, third part, fourth part, fifth part, and sixth part. So it means that for me to be able to walk from this part to this, I need to travel. I have to divide my journey into 6 different parts. 6 different parts. So if I move from 0 to this point, I have just moved 1 out of the 6 divisions, and that is 1/6. If I move from here to here, I have moved 2/6. Moving from here to here, 3/6. Moving from here to here is 4/6. Then 5/6. The last part becomes 6/6, which is the same as 1. Now, your turn to try this. Let's say we have our number line. Our number line, let me divide this number line into some parts. 1, let me divide it 1, 2, 3, 4, 5, 6, 7, 8. Let's start from 0 and end at 1. So let's say this part is 4/7. I want you to complete the rest. Complete the rest. And that becomes your activity. That becomes your activity. Complete the rest. Try this. Now let's move on to the next concept. B. You can also use a paper strip to model and represent the fractions. So for example, let's say you have a rectangle that has been divided into 1, 2, 3, 4, 5, 6, 6. So here, one of the rectangles is 1/6 because the entire rectangle, the division is 6. So the shaded region there is just 1/6 rectangles. Let's look at this one. We have 1, 2, 3, 4, 5, 6, 7. We have 7 divisions. So this part is just one of the 7 divisions, and this part is also another one of the 7 divisions. So in all, we have shaded 2 of the 7 divisions. So the entire shaded region becomes 2 out of the 7 divisions. And that is the answer. Now your time to also try this. Let's say you have a rectangle. Let me use a shape. Let's say we have a rectangle. Um, Let me use this shape for my rectangle. Okay. So let's say we have this rectangle. Let me divide the rectangle into some parts for you. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and the last one is 10. Now let me shade some portions for you. Let's shade some portions for you. So let me use, let's see, I have, okay, so we have this part. Let me clear this part. Let me also clear this part. And finally, let me also clear this last part. Good. So we have, so that is my rectangle. Now write your answer in this box, or write your answer down. What is the shaded region? What is the fraction of the shaded region to the entire rectangle? So find the number of shaded regions and divide it by the total rectangles, and that models a fraction. After that, indicate the type of fraction. Good. Now let's look at the last model. This time we are going to use the Cousinet rod to also model a fraction. Now when we say the Cousinet rod, it is just strips of rectangles with different heights, where each height is just a double of the previous height. So for example, when we take the very first one, when we take the first one, we are taking this rectangle to be 1 out of 6. That is the first one, the basis for our rectangle. This rectangle is 1 out of 6. Now, if I should double this rectangle, it means it's going to be 1 out of 6 plus 1 out of 6. And that gives us 2 out of 6. And that means that the rectangle has to be longer than this, 1 out of 6. Now, when we add another 1 out of 6 to it, that is tripling the first one, gives us 3 out of 6. Then it increases the height of the rectangle. Then we do that, we have to also add another 1 out of 6. So we keep adding 1 out of 6. Then you can see that the numerators will be increasing by 1. Now, when we get to the fifth one, the sixth one, we are going to still add 1 out of 6 to it, and we will get 6 out of 6. So this part is supposed to be 6 out of 6. But we know that 6 out of 6 is also 1, so that is correct. Then we keep adding 1 out of 6 to get 7 out of 6, 8 out of 6, 9 out of 6, then 10 out of 6. We can even continue by adding another 1 out of 6 to it to get 11 out of 6, and so on, and so on. So your activity here is to extend this rods to reach 15 out of 6. Extend it to 15 out of 6. Now, model fractions of similar nature, such as 1 out of 2. So this time, you can also model another using 1 out of 2 as your base. So it means that you will keep adding 1 out of 2 to get 2 out of 2, which will be 1. Then you get 3 out of 2, 4 out of 2, and so on. So you can start with 1 out of 2. You can start with 1 out of 4, 3 out of 7, 5 out of 2. Then you move on, increasing the height in that respect. Now, the benchmark. Fractions are simple, commonly used fractions that are easy to visualize and serve as reference points for estimating or comparing other fractions. The most frequently used benchmark fractions include 0. Now, let's take note that 0 is also a fraction because 0 over 1 is still 0. So it is a fraction. Don't get confused there. Any number at all apart from 0 divided by 0 is 0. So 0 divided by any number at all where that number is a real number except 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 for 1, that is the denominator, being 0, will still give us 0. So whenever you divide any number at all by any number at all, when you divide 0 by any number at all, which is not 0, and a non-zero number, you are going to get 0. You are going to get 0. Let's take note of that. Therefore, 0 is also a common fraction always used. 1 over 4 is a common fraction. Normally, we talk about quarter. 1 quarter, 1 over 4. Then 1 half is commonly used. 3 quarters, 3 fourths is used. And 1 is also a fraction, which is a whole fraction. That is 1 out of 1 is 1. 2 out of 2 is 1. So this is also, these are common fractions that we normally use in our daily activities. So we can still look at equivalent fractions and try and model them. We have looked at equivalent fractions to be fractions that have equal value regardless of its numerator or the denominator. So we can look at 1 over 2, 3 over 6, and 4 over 8. These three fractions are equivalent. Let's check them. Now, first of all, observe that this part here is the same as this entire part, and it is also the same as this entire part. So first of all, we can see that this region here, we can say it is 1 out of the entire 2 divisions. 1 out of the entire 2 divisions. So we have been able to ascertain that this part, the left part here, is just 1 out of the entire division. Just dividing it once, you will get 1 out of 2. Now, if I should divide it again like this, it will not change this value. It is still half. It is still half. So it doesn't change the concept of the half. but it only helps us to rewrite the half in a different way, because we have seen that this part, which was half, now the half has also been divided into two. So it means that it becomes 1, 2, and it has become two portions of the entire four portions. So this part is now 2, and it is now 2 out of 4. It is now 2 out of 4. So we can even write it as 2 out of 4. And that is still another equivalent fraction, 2 out of 4. Now, if we don't divide it like that, there is another way of dividing it. We can divide it this way. So this time, we divide it like this and this. When you do that, it means that the same half, which is here, now it is having three different regions. One, two, three. But it is this same region, which is half. So now it has become three different regions. But it has become three regions out of how many regions? Out of 6 regions, because we have 1, 2, 3, 4, 5, 6. So this same half has become 3 out of 6. And it doesn't change the fact that this shaded region is the same as this region. So this and this are equivalent. And even if we divide it again, then we are going to get 1, 2, 3, 4. In this case, the same region, which is half, now it has become how many regions? 1, 2, 3, 4. It has become 4 regions. 4 regions of how many total regions? 4 out of 8. 4 out of 8. So it means that we are having 4 out of 8, and it is still the same region, which is still half of this. That same shaded region has now become 4 out of 8. So that confirms or establishes the fact that these fractions are equivalent fractions, even though their denominators are different. So we have a lot here. You can analyze this. Half, here it has been divided into 2. So we have 2 out of 4. Here it has been divided into 3. We have 3 regions out of 6. Here it has been divided into 4. We have 4 regions out of 8. And here it has been divided into 5. And we have 5 regions out of 10. And all these are equivalent fractions. Equivalent fractions. All right. Now you have an activity which I will leave it for you to do it. In our next video, we shall look at your answers and also try and solve it. Activity 2.2 is under equivalent fractions matching game. So I will entreat you to pause the video and read through these questions and the instructions carefully. Then you play the game in order to boost your understanding of fractions. Thank you for watching, and see you in our next video. Bye bye.